3.10. We will have another one that is kind of more AP review style, but for our objectives out of our book, this is our last one. So right here, what we're going to be taking a look at is our Taylor and Maclaurin series instead of polynomials. So the nice thing is that we're just really kind of adding on to what you already know. And so that will be kind of refreshing, right? So we'll just be adding to what we already know. So I'm going to start with a definition here of the Taylor-Maclaurin series. And so the only thing that is different is that with a polynomial, it would just end right here, right? So we would just say like, there is our last term. So if we want the third degree, a polynomial n would be 3, end of story. So what is going to happen here is we're just going to extend it. And so this will be our nth term. And so this will typically stay generic. It won't have, you know, a 3 here with a 3 factorial and a power of 3. We'll keep it all just generic. And so that will be called our nth term. So do make sure that you're aware of that language. Okay. And then just like in the past, C is where we're centered, you know, and then our power of 1 over 1 factorial, power of 1 over 1 factorial with the first derivative. So all of that is still exactly the same. We will just now have this added component of what we call the nth term, and we will have this added component of it goes to infinity. Okay, so what does it mean to have the form of a convergent power series? So if we have a function that is represented by this power series, so our functions, remember, are typically like sine of x, natural log of x, that sort of thing. And so if that function is represented by that power series for all values of x that contain that center, and an will be generated by the nth term's derivative evaluated at c divided by n factorial, right? So like that piece there is not unfamiliar to us. And f of x is equal to this guy right here. Okay, so it's really, we're just looking at this as a converging power series as long as the function that we're talking about can be represented by this. So some form of convergence that we will have. Okay, so now let's take a look at our Taylor series. So if the limit of the remainder is equal to 0 for all x in the open interval I, then the Taylor series for f converges and is equal to f of x. Okay, so that is what that piece is saying there. Okay, and again, this is just the nth term that we're taking a look at. All right, so how do we find a Taylor series? Well, the nice thing is it's exactly the same as what we did with a polynomial. We just have this nth term to contend with. And so as far as our steps go, they are not going to be different than what we did with a polynomial. So you will see that piece is exactly the same. So here we're going to find in derivatives. And when we find those in derivatives, we don't really know how many to find in terms of like, but we want to find enough to see a pattern. So we're going to find in derivatives and evaluate them at C. And we're going to do that enough times to see a pattern. Okay, so for this particular problem, so our function is e of x. And we're going to evaluate that at c equals 1, so our center is 1. So I'm going to go ahead and do that at the same time. So I'm not going to find like all my derivatives at once. I'm going to find, you know, just however many I think I need to find in order to see a pattern on this side. And so then at c, so the f prime of x, so e to the x is, derivative is e to the x, and I want to evaluate that at 1. So e to the first is still e. So let's do one more just in case we don't see that pattern. So I'm going to take the second derivative, which is e to the x, and then I'm going to evaluate that at 1 as well, which is e. So do I see a pattern over here? I hope so. Okay, so that pattern is, oh, look, no matter how many derivatives I take, I'm going to get e. So oftentimes, like, you know, questions that come up are, well, what does that mean to see a pattern? So things that will happen would be, perhaps you get, 1, and then you get 1/2, and then you get 1 over 2 times 3, and then 1 over 2 times 3 times 4. So you can see that like you're working with factorials. Another pattern you might see is you'll get 1, -1, 1, -1. So alternating, or maybe you'll get 1, 0, -1, 0, 1, -1, 0, -1, and so on. So at some point you should be able to discover oh, hey, look, something's happening here. And you might have to take, more than just a couple of derivatives. Okay. So then once we get our derivatives figured out, then our next step that we'll be working with is just to follow our pattern that we know for our Taylor polynomials. So we're going to follow that that same rule. Actually, I don't know why I said pattern. Follow the rule that we know from the Taylor polynomial, which applies for the Taylor series as well. So that would be the nth derivative of c divided by n factorial over x minus c to the nth power. Okay. And so let's go ahead and do that. So we have our function, which is e to the x. And so I'm going to go ahead and just start here. So we have e, right? And then that's no derivative, no power. So that would be x minus c to the 0 power of 0 factorial. I'm not going to write that part out. And then now we're going to go to the first derivative. So that would be plus e, and then x minus c, and that would be to the power of 1 over 1 factorial. And then we're going to have e, and then x minus 1, and then that came from the second derivative, so a power of 2 over 2 factorial. And then we're going to go dot, 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 and then we're going to put in our nth term. So then the nth derivative, which is e, and then x minus, not c, x minus 1 to the power of n over n factorial plus dot, dot, dot. And then we want to write that into our sigma notation. So we're writing it into this format here. So then that would be equal to, so I'm just going to now transfer this portion, because that's my nth term, into the sigma component. So that would be e, and then x minus 1 to the power of n divided by n factorial, and then from 0 to infinity. And then if at ever you get to a point where you're like, wait, should it start at 0? Did I do this right? Just substitute in a few terms and see if you did that right. So if you wanted to check to make sure this, this series will generate those terms, just substitute in a few numbers. So to check it to see will that work? So substitute in 0. So you would get e over 0 factorial, x minus 1 to the power of 0, put in n equaling 1, e over 1 factorial, x minus 1 to the first power, and so on. And then 0 factorial is 1, to the power of 0 is also 1. And then you can see up here that, yes, those are the same. And then there you go. Now you have a Taylor series instead of a Taylor polynomial. Okay. So what's the difference between the series and the polynomial is, so this would be our, say, second degree Taylor polynomial, right? Doop, that's it. Just those 3 terms. And then what makes it now be a series is that we are going on forever, and then we've generated a term that will create each of those pieces, or a rule that will create each of those. Okay, so there you go. All right, so these are Taylor series from a basic list. So these are ones that we want to make sure that we memorize. So e to the x, sine of x, cosine of x, and then of course our geometric, which is what we did in 8.9. And so this is more of a generic where a is equal to 1 and our ratio is x, but keep in mind that a and r can be whatever. All right, so for this here, so what we need to know is that this is our Taylor series that will generate a polynomial equal to e of x, or e to the x. And then this right here is our Taylor series that will generate the function sine of x, right? So it will create a polynomial that's equal to sine of x, and then this one right here will create a polynomial equal to cosine of x, and then a polynomial equal to this rational expression that is geometric. So this over here, so this is our term by term, and so we have to be able to work with both. And so this is our expanded form We also will often refer to that as term by term, meaning it's expanded and you can look at it term by term. So if they ever ask you for like the derivative, you can take the derivative of like 1, the derivative of x squared over 2 factorial, but you can also take the derivative of this here as well. And so this is your expanded term by term, and then this is your power series in your sigma form, right? And so this is your nth term that is here, and it should always match there. Okay, so if you ever forget what these are, like if you forget like what is, and these are all centered at 0, by the way. So let me go at c equals 0. If you ever forget what they are, like if you're like, oh man, I forgot, is sine of x is 1 or is cosine of x is 1? So your e to the x is going to be all of them, right? And so if you ever forget, you can just generate them, right? So if you're like, oh man, I don't remember what it is. So you would write e to the x. And then what is f prime? Well, that's also e to the x. And what is f double prime? That's also e to the x. And then it's centered at 0. So then f of 0 would be e to the 0, which is 1. And then f prime of 0 would still be 1. And f double prime of 0 is still equal to 1. And so then I know e to the x is equal to the f of 0, right, using the rule, and then plus, and then 1, and then x minus 0 to the power of 1 over 1 factorial, and then plus, for the second derivative, it's still 1, x minus 0 squared over 2 factorial. And so if I look at the pattern, I can see that the coefficient is always 1, the power and the factorial match, and then there is my e to the x. So if I ever forget, I can always generate these. So let me do one more just to make sure. So let's say we have sine of x. So I know f of x is sine of x, and then evaluate that at 0. And then sine of 0 is 0. And then f prime is cosine. So f prime of 0, so cosine of 0 is 1. F double prime is negative sine. So f double prime of 0 would be 0 because the sine of 0 is still 0. And then I have so many zeros, I'm going to do one more. Derivative sine is cosine. So third derivative, and cosine of 0 is 1. Negative cosine of 0 would be negative 1, and so on, right? And so then my pattern would be this is 0, and then plus the first derivative, and then to the power of 1 over 1 factorial, plus, and then the second derivative is 0, and then minus 1, and then a power of 3 over 3 factorial. And so if you look, there's the x cubed over 3 factorial. I can see that whenever my powers are odd, right, or my derivatives are odd, that's when I generate values of 1 and then negative 1. And so an odd number is 2 to the n plus 1, right, because 2n is even, so add 1 to make it odd. And so like that is to kind of, if you ever forget these rules, you can always run out a few terms to like jog your memory. But you're trying to spare yourself from doing that and just having these memorized because you're going to be using these quite a bit. Okay, so do take that time to memorize what you can for that. Give myself a little bit of room for the problems here. All right, so so what they want us to do now is they want us to find a Taylor series that's going to represent this transcendental function. So like create that polynomial that will be equal to that. And so they want us to do that deriving it from a basic list. So this is pretty straightforward. So what you're looking at for these problems here is you can see that you're going to be working with this. And so for e to the x, so instead of x, it's going to be just replaced with negative 3x because instead of a power of x, it's a power of negative 3x. So everywhere you see an x, you're going to replace it with negative 3x. And so then that's all I need to do. So I have g of x is going to equal, so if I look here, so it's 1 plus, and then instead of x, I'm going to replace it with negative 3x. And then plus, and then instead of x, I'm going to replace it with negative 3x, and then keep it squared over 2 factorial. And then I'm going to run down the line on that. And so instead of x, I replace it with negative 3x, power of 3 over 3 factorial, plus dot, 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 plus, and then instead of x to the n, it'll be negative 3x to the n over n factorial plus dot, dot, dot. And then once you do your replacement, then make sure that you simplify just a little bit. Like, don't go crazy with the simplifying, but you definitely want to simplify a little bit. So I will have 1 and then minus 3x, and then negative 3 squared would be 9, right? So that would be plus 9 over 2 factorial, because I want to get that coefficient. And then over here, oops, that'll be a minus, so let me erase that. And then here I'll have negative 3 cubed, which is negative 27. And then that will be over 3 factorial, and then dot, dot, dot. And then this will become negative 3 to the power of n, x to the n over n factorial. So I'm trying to keep that x term, a little bit isolated there. And then in power series form, just going to start at 0 to infinity, and then I'm going to copy down that nth term. And there you go. As easy as that. All right, so let's go ahead and take a look at this one here. So for this one, I'm going to take that x term and I'm going to replace it with x cubed. All right, and so I'm going to be using the sine function. So I'm going to be looking at this one right here, and everywhere I see an x, I'm going to replace it with x cubed. And then I have that 2 in front as well, right? And so I'm going to go group that out. And so instead of x, it's going to now be x cubed, and then minus, and then x cubed over 3 factorial, right? And then x cubed to the 5th over 5 factorial plus dot, dot, dot. And so again, I'm just looking up here. And so now I'm going to generate my nth term. So again, wherever I see an x, I'm going to replace it with x cubed. So then this would still be negative 1 to the n, and then x cubed to the 2n plus 1 divided by 2n plus 1 factorial, dot, dot, dot. And then I'm going to simplify this just a tiny bit here. So I'm going to work out my powers. So x cubed cubed, so that would be x to the 9th. And then x cubed to the 5th would be the 15th. And then that would be 6n plus 3. So I just distributed my powers. And then finally into the power series sigma form, I'm going to keep that 2 out front and then just substitute in that nth term here. And there you have it. Okay, so then if I want to know what 2 sine of x cubed is as a polynomial, I would just replace each of those indexes, right? So I'd start with 0 and then put in 1, put in 2, and so on. Okay, so here we go. So last one. So x times the cosine of x. So we're still doing the same thing again. So h of x. So I have x, right? And then now times the cosine of x. So just like I had that 2 out front, now I have this x out front. So I would have x, and then now I'm going to look up again. So I'm looking up here to see what is that cosine of x expansion. So now I'm looking right here. And so I don't have to replace x with anything, right? It's just going to be cosine of x. So x times cosine of x, so that would be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot, dot, dot. And then negative 1 to the power of n over 2n factorial, and then x to the power of 2n, dot, dot, dot. So that's just substituted. So 2 was a coefficient, right? Like, or a number value, a scalar. So I can have that pull out to the front, but x is not, right? So that means I do need to distribute that in. So I'm going to go ahead and distribute x into each of those. So x times 1, x squared. Oops, let me leave some room here for coefficient. So I have 1 over 2 factorial. And then x times x squared would be x cubed. And then 1 over 4 factorial, x times x to the 4th is x to the 5th. And then negative 1 to the power of n over 2n factorial. And then this would be to the 2n plus 1. Oops, I don't need that anymore, do I? Lots of oopses today on this one. Okay. All right. And then finally put that nth term into my sigma form. So then that would give me negative 1 to the n over 2n factorial, and then times x to the 2n plus 1. And then that's it. Like that's the end of that. And then from there, we'll have one more video after this, but it is not in our objective. It's just more like AP related, where the questions they ask you are going to extend on each of these topics and challenge you.